Let's presuppose a flat Earth and use right-angle trigonometry for math that won't work on a curved surface. This time to Mount Lemmon, which is about 65 miles away for line of sight. What that means is from my location to the peak of Mount Lemmon is 65 miles. Let's drag the overlay and zoom in. Get a better look here. Those are not clouds, that is snow. That's her right there, Mount Lemmon. This is the T2 Flerf Destroyer. You can see that my 8-minute bubble is plumb. And my plate level is level. That's the snow I was talking about. So if you thought there were clouds, that's the snow. There's a good look. Now let's measure the angle. That's the coincidence bubble. The big numbers up top are degrees. The arrow is pointing to tens of minutes. And then you read minutes and seconds at the bottom. And so the angle that you're reading here is 89, 29, 41. This is the globe Earth prediction. That's the angle. We have to minus from 90. That's the peak of Mount Lemmon. This is where it's appearing. That's my elevation. And that's the distance. So, right angle trigonometry, this is where the peak of Mount Lemmon should appear, is up top there. But it's actually appearing down there. So let's do the math for the curvature of the Earth and see what checks out. What we're going to do is we're going to take our distance and square it, which is going to be 65 miles. Now what we're going to do is we're going to take our 8 inches times a mile squared, and we're going to shave off right around a second and make it 7 inches times the mile squared, just so that we can deal with some standard refraction. So now we've got our distance squared. We're going to take 7, multiply it. We're going to divide this by 12 to get into feet. That's what we need to shave off of the height of Mount Lemmon. So we're going to take 9,167. We're going to roll that up, minus it out. Now we also need to minus out the height of our elevation of 3680. So 3680 minus. Now we're going to divide this by our length in feet. So 343,200 divide. Now we're going to arc tangent that. That's what we have in degrees or decimal degrees. So if we turn that into degrees, minutes, and seconds, it becomes 30 minutes, 16 seconds. But we want to minus this from 90 because that's the zenith. So we're going to take 90.0000. We're going to roll that up. We're going to change this back into hours, minutes, and seconds, or decimal degrees. We're going to minus that. Now we're going to turn it back. I should be shooting an 89, 29, 43. Okay, so the angle prediction, what I would read, because we don't want to read a 54, 57. That's just the angle. But we got to minus it from our zenith, so 90. If we minus this from the zenith, or 90, we get 89.0503. So, there's my coincidence bubble. There's my plate level. And here's my circular level, my vial. And if we look in here, you can see, let me get you zoomed in so that you can see it. My 3 lines are in coincidence on the top. I have an 89 with a 0 minutes underneath it. And down at the bottom, it says 0503. There it is. And let's look through the scope and see where Mount Lemmon is appearing. So well below. This is the field book from yesterday's observation. There's the date, the time, the target, my location. HI is the height of the instrument. That's my height above sea level. There's my approximate distance, Mount Lemon's elevation. That's the flat Earth prediction. This is the angle that's being predicted using this right angle trigonometry. What that means is if I do this math here, this is the angle where Mount Lemmon should be appearing. Here's the formula and how I set it up. This is the angle. We minus it from 90. That's where we point our theodolite, and this is where Mount Lemmon should be appearing on a flat Earth. This is the globe prediction. It's pretty straightforward. We take the 8 inches times the miles squared, shave off an inch for refraction. We take our 65, we square it, we multiply that by 7, we take that result, and we minus it from 9167. Once we have that result, we minus it from our 3680 to get this side of our triangle, which is our difference in elevation. From there, we just run the same formula as we did over here for the flat Earth to get our angle. So this is the angle that the globe would predict. Down here is me computing the error. This is pretty simple. This is the zenith distance. We take the face left measurement that you saw, add it to 360, minus it from the face right, multiply by 1/2. And this gives us the nominal shot of what we shot. Then we take that, which is the nominal shot here, we minus it from what we shot, and it gives us our standard deviation of the error. Then what we do is we take the face left plus the face right, and we find out how much we're short. In this case, it's 9 seconds. So we take that and we chop it in half and we add it to the face left. So now we have a comparison between the nominal and the actual. And so the difference is 1/2 an arc second. This is our instrument error.